A thermal power station using a steam as a working fluid works basically on the Rankine cycle. Steam is generated in a boiler, expanded in a prime mover and condensed in a condenser and feed back into the boiler again. However, in practice, there are numerous modifications and improvements in this cycle with the aim of affecting the heat economy and the increase of the thermal efficiency of the plant. Coal and ash circuit. In this circuit, the coal from the storage is fed to boilers through a coal handling equipment for the generation of the steam. Ash produced due to the combustion of coal is removed and sent to ash storage through a ash handling system. Air and gas circuit. Air is supplied to a combustion chamber of the boiler either through a forced draft fan or ID fan or by using both. The dust from the air is removed before the supplying to the combustion chamber. The exhaust gases carrying a sufficient quantity of heat and ash are passed through an air heater where the exhaust heat of the gases is given to the air and then it is passed through the dust collectors when most of the dust is removed before exhausting the gas to the atmosphere through the chimney. Feed water and steam circuit. The steam generated in the boiler is fed to the steam prime mover, that is turbine, to develop the power. The steam coming out of the prime mover is condensed in a condenser and then fed to boiler again with the help of pump. The condensate is heated in a feed heaters using a steam tapped from the different points of the turbine exhaust. The feed heaters may be mixed type, indirect heating type. Some of the steam and water is lost passing through different components of the system. Therefore, the feed water is supplied from the external source to compensate this loss. The feed water supplied from the external source is passed through a purifying plant to reduce the dissolved salts and to an acceptable level. The purification is necessary to avoid the scaling of the boiler tubes. Cooling water circuit. The quantity of cooling water required to condensate the steam is considerably large, and it is taken either from lake, river or sea. The cooling water is taken from the upper side of the river and it is passed through the condenser, and heated water is discharged to a lower side of the river. Such system of cooling water supply is possible if adequate cooling water is available throughout the year. This system is known as an open system. When the adequate water is not available, then the water coming out from the condenser is cooled either by cooling pond or a cooling tower. The cooling is effected partly evaporating the water. This evaporative loss, this includes the evaporation and the carryover. It is nearly 2 to 5% of the cooling water circulated in the system. To compensate the evaporative loss, the water from the river is continuously supplied. When the cooling water coming out of the condenser is cooled again and supplied to the condenser, then the system is known as a closed system. When the water coming out from the condenser is discharged to river downward side directly, a system known as an open system. Open system is economical than the closed system provided that the adequate water is available throughout the year. The different types of system and components which are used in thermal power plant are listed below. Coal handling system, ash and dust handling system, draft, high pressure boiler, prime mover, condensers, cooling towers, feed water purification plant, different components used as a economizer, superheater, feed heaters, etc. to increase the thermal efficiency of the plant. Working for the thermal power plant. Steam is generated in the boiler of the thermal power plant using the heat of the fuel burned in the combustion chamber. The steam generated is passed through a steam turbine where the part of its thermal energy is converted into mechanical energy, which is further used for generating electric power. The steam coming out of the steam turbine is condensed in the condenser and condensate is supplied back to the boiler with the help of feed pump, and the cycle is repeated. The function of the boiler is to generate the steam. The function of condenser is to condensate the steam coming out of the steam turbine at low pressure. The function of the steam turbine is to convert the part of heat energy of steam into the mechanical energy. The function of the pump is to raise the pressure of the condensate from the condenser pressure 0.015 atmosphere to the boiler pressure of 200 atmosphere. The other components like economizer, superheater, steam feed heater like LP heater, HP heater, steam from the different points of turbine is fed to the heaters to heat the condensate of the heater temperature, are used to primary circuit to increase the overall efficiency of the thermal power plant. Site selection for the thermal power station. The selection of the site for the thermal power plant compared with the hydropower plant is more difficult as it involves the number of factors to be considered for its economic justification. The following considerations should be examined in detail before selecting the site for the plant. The location of the thermal power station should be made with the full consideration not only of the trends in the development and the location of demand, but also the availability and the location of the cheapest sources of the primary energy is also considered. The few important factors to be considered for the selection of site for the thermal plant is discussed below as the availability of the coal. The question of using a diesel or a gas for thermal power plant in India does not arise as these sources are limited. The major source of energy which is available in India for thermal power plant is coal. Therefore, it is necessary to concentrate for the best use of coal for power generation. The huge quantity of coal is required for large thermal power station. A thermal power plant of 400 megawatt capacity requires a 5,000 to 6,000 tons of coal per day. Therefore, it is necessary to install a power station near the coal mines. In this case, the power generation must be transported through a long distance. Therefore, it is necessary to find the location which gives the lowest cost considering the coal transport and the electrical power transmission charges. The Energy Survey Committee of India has suggested the use of byproducts of the coal for power generation, which are commercially unusable products resulting from the process of washing coal, where the washed coal is essential for the metallurgical industry. The committee further pointed out that with the increased washing of the coal, with the development of steel production, vast amount of middling would accumulate at the coking coal fields, resulting the problem of disposal of such waste. The estimate made by the committee as the byproduct of coal is about 4.86 million tons in 1973 and that out 9 million tons in 1980-81. Ash disposal facilities. The ash removal problem has become more serious, particularly in India, because the coal used for power generation contains a large percentage of ash, that is 20 to 40%. The quantity of ash to be handled is as large as 1,500 to 2,000 tons per day. The ash handling problem is more serious than the coal handling because it comes out in a hot condition and it is very highly corrosive. Its effect on atmosphere pollution are more serious than the human health is concerned. Therefore, there must be sufficient space to dispose of large quantity of ash. A 400 megawatt power station requires nearly 100 hectares area per year if the ash is dumped to the height of 6.5 meters. The disposal of a large quantity of ash from the power station, if the site for its disposal at the plant is not available, also becomes a serious problem. In addition to the mounting problem of ash disposal at this power station in the large cities like Delhi, Bombay and Madras, there is also serious problem of the pollution arising from the fly ash. This is already become a problem attracting much attention with respect of thermal power station at Delhi to extent that Government of India has set up a committee to study the measures to be taken for mitigating this problem of health hazard in the city. The ash can easily dispose of to river, sea or lake economically if such facilities are available at the plant site. Presently, the ash from the power plant is used for many industrial processes. Therefore, the question of its disposal to sea or river does not arise. The space requirement. The space and the building requirement by the power station is another point to be considered. The average land requirement is 3 to 5 acres per megawatt capacity, which includes the space required for coal storage, ash disposal, staff colony, market facility, and the space required for whole machinery. Generally, the space occupied by the 10% for building, 33% for cold storage, 27% for cooling tower if any available, 7% for the switchyard, remaining 23% for other purposes. The percentage may also change slightly according to the surrounding condition. The cost of the land adds in the final cost of the plant. Therefore, it should be available at a cheap rate. The large plants in the heart of the big cities and near the center of the load are not economical as the cost of land is very high. Now fourth, nature of load. Nature of land. The selected site for the power plant should have the good bearing capacity as it has to withstand the dead load of the plant and forces transmitted to the foundation due to machine operation. These are number of cases where the plants have failed due to the weak foundation. The minimum bearing capacity of the load should be 10 kg force per centimeter square. Availability of water. Large quantity of water are required for condenser, for disposal of ash, and as a feed water to the boiler, and drinking water for the working staff. The quantity of cooling water required in the condenser, condensing the steam coming out from the turbines of 60 megawatt capacity plant, is of the order of 20 to 30,000 tons per hour if it is discharged to the lower side of the river. If cooling tower are used, then the makeup water require also 500 to 600 tons per hour. The water required to feed the boiler owing to the losses in the system is also as large as 6 to 10 tons per hour for the 60 megawatt capacity power plant. This water must be as pure as possible to avoid the scaling of the boiler tube, which is generally demineralized water. The large quantity of water is also required for disposing of the ash if hydraulic system is used. It is therefore necessary to locate the power plant near the water sources which will be able to supply the required quantity of water throughout the year. The availability of a drinking water is also equally important as the 1000 megawatt capacity plant requires 1 million gallons of fresh water per day. Transport facility. Sixth one. This is another important consideration and locating the thermal power station. It is always necessary to have railway line available near the power station for bringing the heavy machinery for installation and for bringing the coal to the power plant. It is always thought that the site of a thermal power plant near the coal pit head is more economical than the selecting a site near the load center. In this respect, it would be interest to know the statement made by the late Dr. Baba in Geneva conference that it will be seen that at least 75% of the country is devoid of coal, while some 55% of the coal reserves and 80% of the present production in the state of Bengal and Bihar. This has to consequent the coal is often hauled over a distance of 1,500 miles to the areas of north and west and south. Even when the central India coal fields are fully developed, coal will still have to be hauled over a distance of 700 miles to areas of south and west such as Bombay, Ahmedabad, Punjab and western UP to north. Thus, a million kilowatts of capacity in coal-fired station at a distance 700 miles from the nearest coal field would invoke the transport of 3.6 million tons of coal over this distance, and this will lock up some 10,000 wagons and 165 locomotives, representing a capital investment of around 175 millions. Another reason in locating a thermal power plant at a pit head is there is every possibility of a danger arising from the dislocation of coal through a lockouts and strikes in the railways. Also, in event of any war emergency, the transport capacity is unavoidably tied up in moving the coal for the power generation. As against the modern transmission lines are so constructed that the maintenance required is very less. Therefore, the operating cost of the transmission line can be stated to be practically unaffected by the rise of wages and material cost. while the same is not true for the transport, as evident from the frequent increase in the freight rates. Availability of labor. Cheap labor should be available at the proposed site, as enough labor is required during the construction of the plant and the working of the plant. Public problem. The proposed site should be far away from the towns to avoid the nuisance from the smoke, fly ash and heat discharge from the power plant to the residential people. Now the size of the plant. In small capacity plants, the cost of getting fuel into the plant and easy of water supply is relatively insignificant factor, and the problem of the plant location reduces almost entirely to an electric transmission problem. Other thing being equal, the plant must be located at such a point that the investment in the electrical cables for transmitting the power together with the annual operating cost should be minimum. In such location takes plants away from the point of fuel supply and water supply or both. The supply saving in the electric transmission may be more than the offset by extra cost in fuel and water supply. Therefore, it is necessary to determine the relative significance of these items before selecting the site for the power plant. The expenses involved in the electric transmission from small plant are relatively severe owing to the impracticability of using the high voltages, so that the electric transmission feature alone become dominant in the power location. In case of a large capacity plant, the cost of transporting enormous quantities of coal and the water are considerably high. Therefore, the plant must be located near the pit head, provided a required water quantity is most available as near as possible. A very slight difference in the temperature of the available condensing water makes so mark a difference in the performance of the steam turbine that a change of location of a few kilometers may easily justify the greater electric transmission expenses involved. The large power plant must be located close to the railroad offering the adequate services, because the cost of railroad tracks construction is so great in comparison with the cost of electric conduits to or overhead lines as overshadow any expenses involved in the electric transmission against the coal handling. The economic significance of a large plant compared with a small one is much greater than the mere ratio of size, because of the large station will be likely to supply a community whose interests are so involved and so dependent on the continuity of the service that the coal supply must be absolutely continuous. It would be fatal to have a coal strike or railway strike even for one day. Therefore, plant